Guys, hope all of us are doing great. My name is Ernest, and this is Ernest Sciences and Mathematics TV channel. So in this specific discussion, we're going to look at the concept of complex numbers, and this basically is going to entail the concept of complex numbers from the definition perspective. So therefore, it's going to assist us to differentiate what we basically refer to as complex real numbers. And in this case, of course, I've discussed the role of or different types of numbers in one specific video, which I'm going to put a link in the description box. So therefore, we are going to confine ourselves to, of course, the algebraic representation of what we refer to as complex numbers. Now, in our last discussion on the concept of what we refer to as the quadratic equation, we had said that we can be able to represent the value of x using, of course, this specific equation, which generally represented the standard form of a quadratic equation, which was given as such. So I said that we can be able to have a general form of a quadratic equation using the formula plus bx plus c, which is equivalent to 0. So I'd said that the concept of this specific quadratic equation, we're going to have it as a, b, c, which are going to form a set of real numbers, where of course a is not going to be equivalent to 0. So in some cases, as I said, this specific quadratic equation is going to assist us find roots of numbers, or rather to find roots of these specific values of equations. And in this case, I'd say that we can be able to use three basic methods in trying to find roots of quadratic equations. The first one I mentioned is factoring methods. The second is completing a square method. And lastly, we can be able to use the concept of a quadratic formula. Now, in some cases, we're going to see that in trying to solve these quadratic equations, some situations are encountered whereby the concept of a discriminant, which I had mentioned, is going to be having a negative number, and therefore that is going to be dictating the nature of roots that we're going to find. And these roots are going to be non-real roots or imaginary roots, as we said. For example, if we can consider the case of a number whereby we have specific values for this specific equation, whereby we're going to do a substitution and find that this particular part of the discriminant is a negative value, and therefore we're going to have this particular equation giving us non-real or imaginary roots. So in order for us to find the meaning from these specific roots of negative numbers, we're going to employ what we call complex numbers, which of course are going to assist us describe the roots of these specific, of course, what we refer to as the specific equations. So therefore, with this one in mind, the concept of complex numbers is going to be a set of numbers which are going to assume the form of a plus bi. And in this case, of course, a and b are going to be, or a and b are going to form a set of real numbers, whereby this I is going to be what we refer to as an imaginary part. So therefore, we can be able to represent a complex number using this specific format. And the concept of I basically is going to be equivalent to the root of a -1. And therefore, we can be able to represent I as the root of a -1, as I've said. And this is going to have an implication of the root of the square of I being given as -1 given as such. So suppose we consider the case of this specific representation for an imaginary number. The number a is going to be a real part, while the number, the section of bi is going to be an imaginary part. So this is going to be more elaborate, especially when we're going to express these specific numbers in form of a graph, whereby we're going to, of course, employ the concept of a Gantt diagram. And this is going to assist us, of course, in trying to display, of course, this, or rather illustrate this specific concept of real numbers and imaginary numbers in terms of a graph. So this particular form that I've given of a plus bi is going to represent what we call algebraic form of the complex numbers. So in some cases, we're going to see it being referred to as the Cartesian form of this, of course, complex numbers, or in some form a rectangular form of these complex numbers which we're going to encounter in some literature. Now, as we have been expressing various parts of the equations, and in some cases we're going to be required to find roots of course, coordinates which are expressed in forms of a polar form, and of course this is also going to be applicable in terms of course, the complex numbers respectively. So I'd like to invite us to check on the concept of real numbers and the concept of a Gandhi diagram, which basically is going to give us a graphical representation of these aspects of real numbers. But I hope that the concept of real numbers of course comes into play whenever we are going to see that part of the solutions of this quadratic equation are going to give us non-real roots, and of course these non-real roots requires us to represent them and of course derive meaning using this specific aspect of complex numbers, which has this general representation, and we can be able to display or rather give a notation for a complex number given us the root of a -1 as such. So we're going to see various forms of complex numbers and how we can be able to perform various operations insofar as complex numbers are concerned in our next video. So that is it for now, guys. Bye, God bless you. Catch us in our next video.